Hi guys, welcome to the second part of the class on mobility. Today we're going to cover the foundational concepts needed to understand mobility. In this first lecture, we will mostly focus on steady-state gait. The knowledge that's needed for this part of the class includes some of the material that we covered last semester when we were studying the biomechanics of gait. So, what is mobility? In the context of understanding the functions that support basic activities of daily living, mobility includes gait, transfers, bed mobility, and stair walking. The concept of mobility also encapsulates various aspects of the control of locomotion, including the ability to initiate and terminate gait, the ability to adapt gait in order to avoid obstacles, and the ability to adapt the speed and direction of locomotion as is needed. In people's everyday lives, mobility often involves navigating through complex and often cluttered environments, while also performing varied tasks. Moving through the complex world outside the clinic or the laboratory can require frequent changes in body posture and a constant monitoring of your surroundings. It can also involve various forms of transportation, from walking to running to using a bicycle or a car or a bus or a train. It can also require carrying, moving, and handling objects. In our first lecture, we'll be mostly ignoring all of the real-world complexities of mobility, but we will return to them in the next lecture. Here we have a quote from Aftab Patla. Aftab Patla is a scientist whose work we will encounter a number of times in this part of the class. Here in this quote, he is identifying a truth regarding the current state of scientific knowledge regarding mobility. We know a lot about gait, but very little about mobility. This reflects the fact that a vast majority of research on mobility is derived from the analysis of gait in specialized laboratories. Laboratory gait analyses often have the purpose of trying to identify and describe the key characteristics of the normal gait pattern. They also frequently have the goal of attempting to uncover the basic mechanisms that underlie the control of gait. The highly controlled contexts of laboratory and clinical settings contrast sharply with the varied challenges for mobility performed in complex environments and real-world situations. We will begin exploring some of those challenges in later lectures. We can think about mobility through the International Classification of Function framework developed by the World Health Organization. The diagram on the right here is from the textbook. It depicts how mobility can be thought about within this framework. So let's move through some of the components of the ICF model. A key body function of mobility is the ability to produce a gait pattern. That is, to produce a coordinated movement that allows for the movement of the body through the environment. A good example of a mobility-related activity is assessing mobility via a 2-minute walk test. This test is performed in the clinic, on level firm ground, and most typically in a well-illuminated environment. In contrast, an example of participation would be the ability of a patient to take their dog for a walk in the local park. Contextual factors in the ICF model include environmental factors and personal factors. An environmental factor for mobility would be terrain characteristics. Personal factors for mobility include things like age, sex, and self-efficacy. We can also understand mobility in the context of the systems approach model. As we've discussed previously, in the systems model, movement is assumed to emerge from a context of constraints. This context of constraints includes subsystems within the individual, environmental constraints, and attributes of the task. If we think about the attributes of a task, we can think about where we are in the class at the moment, and also where we're going to be going in this class. The basic attributes of the basic attributes of a task are stability, mobility, and manipulation. We've just finished learning about stability, that is, the ability to regulate the posture of the body. Mobility is what we're going to look at in this next part of the class, and manipulation that we're going to look at in the final part of the class are only possible when posture is stabilized. So, movement tasks typically have certain stability, mobility, and manipulation constraints. For example, if a person that you're working with is having difficulties working in the kitchen, it could be because that person has poor standing balance. It could be that because they have poor reaching control, or it could be because they have poor hand function in terms of how they're able to utilize kitchen utensils. As with the first part of this class, our goal will be to understand mobility from within the framework provided by Shumway, Cook and Woolacott. Our first aim is to understand the contributions of individual, task and environment to various mobility functions. Our second aim is going to be to understand the requirements for and strategies that support successful locomotion. If we wanted to create a list of the key characteristics that would capture the notion of mobility, what would we put on that list? The essential aspects of mobility can be taken to be progression, postural control, and adaptation. Progression includes the ability to produce a locomotive pattern, to initiate gait and terminate gait, to change the direction of progression, and to guide locomotion towards distal goals. Postural control involves both postural stability and postural orientation. In the context of understanding mobility, postural stability concerns controlling the center of mass relative to the now constantly transforming base of support. And postural orientation concerns dynamically aligning body segments relative to one another and the environment. Lastly, adaptation involves the ability to adapt the strategies that are used to accomplish progression and postural control to the changing demands of the task and the environment. When we consider the postural control requirements for mobility, we can draw upon the concepts that we've already studied when looking at standing balance. In the context of mobility, an example of steady-state balance is seen in the task of walking at a constant speed, walking under constant velocity conditions. Reactive balance and anticipatory balance refer respectively to the adjustments that are made to counter unexpected and expected internally and externally generated destabilizing forces. Here we see a footballer being unexpectedly pulled backwards as they're attempting to run forwards. We also see a person stepping up and over a log as they're walking down a forest path. In the first example, the footballer must react to the pull. Given that this is football, this probably means that the footballer will now proceed to dive on the ground and start pretending that they've been hurt really, really badly. But that's a little bit off topic. In the second example, as the person approaches the tree laying across the path in front of them, they're able to anticipate the challenges to balance posed by this part of the environment, and they're able to adapt their locomotion in order to step up and over the tree. One of the reasons that we know much more about locomotion in laboratory settings than we do about mobility in real-world settings is that it is far more challenging to study mobility in people's everyday lives. One nice example of some research attempting to study mobility in real-world settings comes from a study of Anne Shumway Cook's. Anne videotaped trips taken into the community by older adults. For each subject, a video recording was made of a trip to the grocery store, a doctor's visit, and a recreational trip of some kind. The video data was analysed to reveal the average and common characteristics of trips out into the world. What was observed in this study was that the average distance walked on each one of these trips was about 360 metres, or about a quarter of a mile. Measurements of illumination levels during these trips showed that trips were on average very well illuminated. 18,000 636 lux, it corresponds to a light level that's similar to standing just out of direct sunlight at midday when the skies are clear. Somewhere between 1 and 2 packages were on average carried. The average weight of packages was 6.7 pounds. Okay, when we look at the analysis of video recordings in this study, we find that about 28% of trips into the community involved needing to open a door manually. About 47% of trips required that 2 flights of stairs had to be negotiated. 42% of trips required that a curb must be negotiated. 42% of trips had slopes or ramps that needed to be negotiated. 60% of trips had uneven surfaces that need to be dealt with. On 13% of trips, there were obstacles that would need to be walked around or stepped over. On 6% of trips, there was the need to avoid adjusting mobility to avoid colliding with another person. On 7% of trips, it was necessary to cross a busy street with traffic lights, and on 35% of trips, it was necessary to cross a busy street without traffic lights. Lastly, distractions in the environment were seen on 58% of trips out into the world. An example of a distraction in the environment would be walking past an area with heavy construction noise. Shumway Cook and colleagues also performed a fine-grained analysis of the recordings that were made of participants going to the grocery store. They looked at 10 minutes of video and coded up the postural transitions that were observed during that 10 minutes. In the 10 minutes of video, they on average observed 4.3 times when it was necessary for the participant to change their head orientation, 0.78 times on average when it was necessary for the participant to have to back up, 4.3 times on average when a change in facing direction of the body was needed, 1.2 times on average when it was needed for the person to reach forward, 0.7 times on average when it was necessary to perform an upward reach, and 0.48 times on average when it was necessary to perform a reach down. Let's turn now to considering steady-state gait. We'll spend nearly all of our time in class looking at walking. The reason for this is simply because walking is the most typically used gait pattern. So, the first thing that you might want to ask is, why is walking the typical gait pattern? Walking is typical for healthy young adults because it represents the most stable form of movement in the typical context of constraints. We can gain an understanding of this by thinking about the gait patterns that are preferred when the context of constraints is non-typical. If you change the environmental constraints on gait by changing the pull of gravity on the body, you will see a different gait pattern emerge. On the moon, bunny hopping and skipping are the typical gait patterns. If you look at children that have much lighter bodies than adults, you will sometimes see that skipping will emerge as a preferred stable gait pattern. This hints at the relevance of body mass as an important individual constraint. Unna-Tan syndrome provides a glimpse into other constraints that affect why a particular form of locomotion becomes typical. Persons affected by this syndrome have been found to walk on all fours. Unna-Tan syndrome is a syndrome proposed by a Turkish evolutionary biologist named Unna-Tan to classify the symptoms he observed in a family that he observed in southern Turkey. Investigations of Unna-Tan syndrome suggest that there are neurological, genetic, and potentially even socio-cultural factors that underlie why people in this particular family locomote quadrupedally. I provided links to videos and documentaries that show these particular gait patterns in action. For your entertainment, I've also provided some links to some wonderfully random examples of non-typical gait patterns. I do apologize if they end up sending you down some bizarre internet rabbit holes. Much of this part of the class is going to focus on walking, and will build upon quite a bit of the knowledge that we developed last semester in looking at walking in the functional biomechanics class. Given the overlap in material between the biomechanics class last semester and this class, I'll only touch on the material that we've covered in detail before. Make sure that you refresh your knowledge of the relevant concepts if it's faded. So, here we have the walking gait cycle, typically considered as occurring between consecutive heel strikes of the right foot. Here we have the distinction between stance and swing phase, and as if you recall from last semester, we see that the proportion of time spent in double support is decreasing with walking velocity. Here we have the terminology that's frequently used to identify the different subphases of the gait cycle. And here we see the distinction between double support phase and single support phase. As you might recall from last semester, the proportion of the gait cycle that's spent in double support phase is going to decrease with gait speed. The distinction between single and double support phase is functionally significant. The double leg support phase conveys increased postural stability. The base of support is larger during the double support phase, and the center of mass is always located within the base of support during the double support phase. The stability conferred by double support phase is also revealed in the results of cognitive dual tasking experiments. Here we're looking again at an experiment that was conducted by Lohoy and colleagues. If you recall, participants said the word top as fast as they could after hearing a sound. They observed that reaction times were far quicker if they had to react to the stimulus during the double support phase. This suggests that double leg stance requires less cognitive resources to support postural stabilization. Last semester, we reviewed some of the laboratory-based evaluations of gait cycle parameters. This research suggests that the average stride length is approximately 144 centimeters, and the average stride duration is about 1 second. The data on gait cycle parameters that we reviewed last semester were based upon assessments that were performed within the controlled environment of a laboratory. Consistent with the systems approach, field studies have revealed how gait parameter preferences can be affected by changes in the naturally occurring context of constraints. In this particular field study, the researchers studied people crossing a signal-controlled crosswalk. They observed about 7,000 pedestrians crossing this crosswalk, and about 3,500 of them were 65 or older. In this research, younger adults were observed to cross the crosswalk much faster than older adults. And crossing speeds were much faster when there were shorter pedestrian crossing times on the crosswalk signal. Consistent with the systems approach, what we're seeing here is that gait cycle parameter preferences depend upon age-related changes in the constraints of the individual and in changes in the task constraints associated with the permitted crossing times. Other field study evaluations of gait parameter preferences have shown that gait speeds vary with the town, city, or country that you live in. For example, average walking speeds measured in downtown areas of major cities suggest that walking speeds in the US are about 1.52 meters per second. In contrast, in Brazil, average walking speeds were found to be about 1.1 meter per second. As I said earlier, there's a significant overlap between what we're covering in this part of the class and what we covered last semester when we were looking at the biomechanics of walking. Your goal in studying for this class should be for you to get to a point where you're comfortable describing the basic kinematics, kinetics, and muscle activation patterns associated with a walking gait. The goal here is for you to understand the form of the gait pattern and the associated function that goes along with that form. To do this, you should review material on gait cycle kinematics and muscle activation patterns from the biomechanics class. I've included much of the relevant material in your slides handout for this class. You will also find this content covered in the textbook. You should review this material before moving on to the next video lecture. In the next class, we'll look at the basic kinetics of gait. When you're working through this material, you should keep in mind how representative or generalizable the knowledge that you're learning is. Gait kinematics have good generalizability. This means that you can expect the gait kinematics to be quite similar across many healthy adults that you look at. Kinetics and muscle activations, on the other hand, have less generalizability. This means that you are likely to observe variation across people, and even across the same person on different occasions. Part of the reason for this is related to the concept of adaptive covariation that we encountered in the first part of the class. Okay, that wraps up this lecture. In the next lecture, we'll be looking at gait kinetics and theories of what makes gait efficient.